In this video, we're going to practice using Lane's binomial calculator, and we may contrast it with the Poisson calculator, which is available on a website called StatTrick. Okay, so we're going to start out by looking at these problems. All right, so if we roll a die, that's the singular of dice, 20 times, how likely are we to get a 4 3 times? How likely are we to get a 4 3 times or more? How likely are we to get a 4 at least 3 times? Okay, so first of all, we might ask, well, is this a binomial problem in the first place? All right, well, there's a couple of things we want to look for. First, we want to see if there's like a constant number of trials. Notice we're rolling this dice 20 times. Now, another thing we need to ask is, does the probability of a success change through those trials? So notice that a success for this particular set of problems is the 4 coming up. So in other words, 5, 6s, 2s, 3s, and 1s, those are failures. So does the probability change? Well, as long as the dice aren't weird or something, it should be 1/6 every time. So there's basically, if you divide 1 by 6, you get 0.167, etc. So that should be the frequency of a success, or the probability of a success, every time you roll the dice. Okay? All right, so those two things are satisfied. Okay, so is this a binomial problem? Does it violate the requirement of only one outcome? Well, there are other outcomes, right? 3, 5, 2, those are other outcomes. Remember, another thing about a binomial is there can really only be 2 outcomes. There can be a success or a failure. However, we can use binomial here because we can group all those other outcomes, like 3s, 2s, etc., as failures. And the probability of a failure is 5/6, right? Okay. All right, so yes, it's a binomial. No, it doesn't really violate this requirement. Gain of 4 is a success with a frequency of pi equals 1/6 or 0.17. All right. All other scores are failures. Okay, so how do we answer these questions? All right, so what we want to do, you could try and use simple probability to answer it, but it gets really, really complicated when you have a number of trials, and it's much easier to use the binomial calculators. All right, so let's first take a look at where the binomial calculator is. All right, so if you look at, this is Lane's book. He has a section called Calculator. When you click on that, you get this selection of several calculators. Notice the binomial distribution is the third one, so you select that one. Okay, so here we're looking at the binomial calculator. What we need to do is we need to put in the number of trials. That's what n is. So remember, we had 20 trials for this one. All right, we're rolling the dice 20 times. And then we need pi. So pi is the fixed number of successes, or the rate of success. So what we want to do is we want to avoid rounding errors wherever possible. So one thing some people might do is they might put 0.166. See, that's all. It only holds 3 decimals or 3 numbers in here. So to avoid a rounding error, drop the 0. Just put period 166. See, I got another digit in there. Okay, but that one needs to be rounded off. Okay, so that's the best we can do. Okay, now let's consult the question one more time. All right, so let's do this one first. how likely are we to get a 4 exactly 3 times, basically? We're going to answer that one. All right. So to get an exact number, first of all, notice the shape of the distribution here. So this is not symmetrical. Okay, why is that? Because the probability is pretty far from 50-50. All right, so as you're going to find out with the Poisson distribution, if you have probabilities of, 0.5, all right, notice how they tend to be symmetrical like that. But when you get far from that, like 0.8 here, like an 80% probability, it starts getting a weird shape. And that gets more weird the higher you go. See how here's 0.9. And we were at the other end, so you already saw that. All right. I'm just going to put this back in there. Okay. So what we wanted to find out is we wanted to find out the probability of getting a 4 exactly 3 times. So what that's going to be, now the area under this distribution is 100%. So those are all the possible outcomes. This is essentially everything that could happen when you roll the dice, 20 times. And remember, these are the times that 4s come up, okay? So you may notice this one here, that's the, the median score, I guess, or actually the mode of this distribution. The average of the distribution would be the number of trials 20 times 0.167, if you wanted to find out what that is. And it's going to probably be close to this score here, so you can see that looks like it's at about 3, I think, or something. Okay, so what we want to do then is we want to find out exactly 3. So between 3 and 3. There it is. Okay, so that's what I thought it might be. That happens to be the average as well. All right, so, or the mode. So 3 is the, the most likely number of times the 4 will come up. How likely is that to happen? So here's the probability. What that means is if you roll the dice 20 times, the 4 is going to come up 3 of those times about 23% of the time. So that's, what the most likely outcome is going to be. About 23% of the time you're going to get a 4 3 times. Okay, but sometimes you're going to get the 4 4 times, 5 times, etc. All right. So that's the probability of getting exactly 3 times. And the way you get that is you click this between button and you have to put in 3 in both of them because it's inclusive. So notice another nice thing about the binomial distribution in Lane is you can kind of look at this graph and see what's happening. Notice how we just have the score of 3 is shaded red. And that's what we were looking for. Okay, so this is the 3 trials that the 4 comes up. All right, what if we wanted to know how likely it is to get, let's see what the other questions are. I guess I'll do the actual ones here. So there's the answer rounded off. All right, usually we round things off to 3 decimals. So let's see, how likely to get a 4 3 times or more? 3 times or more. Okay, so we want the 3, but we want everything above that as well. So for that, what we need is we need above 2. So notice you don't put 3 in there. You see that? See how the 2 is shaded? We want everything above that. Notice the 3 is in there and it's shaded. Okay, so here's the probability. So usually you're going to, if you roll the dice 20 times, the 4 is going to come up 3 or more times about 67% of the time. Okay? All right. What about below? Or let's see what the other question was here. Okay, so that's 67. All right. How likely to get a 4 at least 3 times? Okay, at least 3. So at least 3, we want a 3, but then a 4, a 5, or a 6 would also be at least 3, wouldn't it? So I put this in here just because I wanted to show you there's more than one way to ask a question. This is actually the answer for that last question as well. Notice that it's asking the same question as the other one was. Okay, well, let's look at a new scenario. All right, so this time, and I frequently use butterflies to illustrate this because we're trying to make this course as biological as possible. You know, Lane is a psychologist, I guess. All right, so a lot of his examples come from the field of psychology. So I've tried to make mine from the field of biology. So let's say you're studying these 2 butterflies. These are called, well, this is the monarch, this is the Gulf fritillary, and we're kind of curious, do they like roses or not? We're interested in whether they're good pollinators of rose bushes. Okay, so we might start out if we knew, for example, how common these are in the area. So let's just say we've got, years of data to back this up, and we know that, in Davie, monarchs are about 30% of the butterflies. That's sort of a given thing. All right. We're kind of curious, well, do they like roses? Or what do they think about roses? I mean, they could be avoiding roses, or they could be attracted to roses, couldn't they? And we can answer, we can do both of those things or address both of those things. Okay, so you may notice that this 30% here, this is based on years of data. It is a parameter. Okay, it's not a statistic. That is a parameter. Remember, a statistic is just based on a sample, whereas a parameter is based on the population. Okay, and that's what we're actually putting into these binomial calculators. Now, here's something else I'm going to go ahead and throw out. This chapter doesn't really talk about hypothesis testing. It's going to be a while before we get to that. But you've probably had some hypothesis testing in other statistics classes you've taken. And since we use that so much in biology, it certainly doesn't hurt to start laying the groundwork here. So what we do with these analyses, we're kind of asking how probable things are. And the sort of the scientific process, we usually start out with statements, and then we try and disprove them. That's what we really do in statistics. So in this case, you might say that the butterflies, the monarchs, are neither prefer nor avoid roses. Okay, so in other words, they're just going there at random. And if you think about what we're doing with the binomial distribution, we're actually modeling this random scenario here. In other words, if they're 30% of the population, then 30% of the time they're going to be going to roses, right? If they have no preference, they just go there at random. So that would mean that if you counted butterflies all day, 30% of the ones on, or close to 30% of the ones on roses, are going to be the monarchs if they're 30% of the population. Okay. All right, so we're going to focus on monarchs first. So let's kind of generate a little experiment here. Let's say we go out and we sort of look at our roses, and we're watching these butterflies coming in. So we count 80 butterflies total, and we kind of keep track of what species goes in there. You've got fritillaries going in there, you've got skippers and all these other species of butterflies. But 20 of the butterflies that came to the roses were monarchs. Wow, that's pretty high. I mean, it's not exactly 30%, is it? So how likely would that be, given that the parameter is 30% of the population? All right, so what we're going to be doing then is we're going to kind of model what would happen if everything was random, and then we want to say, how likely is this score? You see what I mean? So how likely is this data or this observation given this parameter. Okay. Well, first of all, let's take a look at something. So the mean of the binomial distribution is the probability, all right, times n. Okay. So actually, I've sort of switched them, but that's the probability, 0.3. All right, that's the parameter. And the number of trials is 80. Okay, so 24. That's the most likely thing that would happen in 80 trials. So all things being equal, if you counted monarchs all day, you would expect about 24 of them to go to the roses if they have no preferences. Well, let's see how likely this is then. So we can do the same thing we did before. All right. So we put in our number of trials, 80, and then we have our fixed rate of success. This is the parameter, 0.3. Okay. Now, what we wanted to know, well, what if we wanted to know exactly how likely exactly 20 is? And these are the types of questions Lane is going to be asking you when you're practicing this stuff. So exactly, the probability of getting exactly 20 butterflies in a count of 80, that's pretty low. But that's not really, that doesn't really get at our question. You know, that's kind of a single event. I guess you could look at this distribution. So this is what these butterflies will do if they're going to the, the flowers at random. If they're going at random, well, the most likely score is 24, but this is kind of up here close to the middle too. I mean, these scores here in the middle are what's likely to happen. This is the extremes at the end. That's what we're really interested in. So if the monarchs are avoiding the flowers, you're going to get scores over here, right? Or maybe even over here. If they prefer the flowers, you're going to get scores over here or over here, all right? So that's what we're interested in. We want to know what these probabilities are to determine whether or not they prefer them. Okay, well, let's see if they're avoiding them. What would it be? Well, then what we need is below 21, right? Because that has our score of 20, but it also has everything over there. Well, if they're avoiding the flowers, there's like a 20% chance that you could get a score of 20. So that doesn't really seem so unlikely to me. I mean, remember, this is showing us here. This is showing us how likely it is those butterflies are going to go to this rose, these roses, I guess. And so they might go there, 20%, getting a score of 20% or at least 20%. There's like a 20% chance of that, or 20 times, there's like a 20% chance of that happening. So that's pretty likely. All right, so it doesn't really look to me like they're avoiding the flowers. If they're avoiding the flowers, this probability would have to be really, really low. In other words, it would have to be really, really unlikely that they go there at random. So let's talk about what this is again. Really, let's be really careful with this now. So what we've shaded in here, this red area, that is that probability. Remember, the whole thing is 100%. And this is the probability that these butterflies will go to the roses, all right, 20 times or fewer, given this, parameter. So if they're going there at random, you're going to get scores in the red area about 20% of the time. All right? But the thing is, what we're asking, another thing we might be interested in, well, how likely is it that they are going to avoid it? Now, this is a little more tricky, okay? So notice that we said the average was 24, and 20 is 4 points, I guess, below 24, right? So what about above, like 28 would be the other extreme? So now what we're doing is we're asking kind of a different question. So instead of, all right, So now what we want to know is how likely is it that we would get a real extreme score like this? So in other words, what we're interested in is a score this extreme on either end. Like how likely is it that it would be 20, like really a low score, or 28, an equally far high score? All right, so let's try that. So to look at the other end, all right, we're going to need above 27, aren't we? Okay, because we want 28 to be in there. So there's the other end. Now you may notice this probability is pretty close to the other one because it's almost symmetrical. And that's because we have such a large sample size. So it tends to be more symmetrical as we get close to a pi of 0.5 or as we get larger sample sizes. Okay? All right, so let's see here. So if we wanted to know, well, how likely is it that we would get extreme scores given that they're going at random? So here we've got we're modeling the random count, right? And the extreme scores would be 20 on this end, 28 on that end. We need to add the two probabilities. So a quick way to do that is to just copy the probability like this and then put it into, paste it into an Excel spreadsheet. And I've done that here, like that's the upper one, here's the lower one, and then you can just sum the two in your Excel spreadsheet. So I get, 0.393. And that's what I wrote as a conclusion on this slide. So, conclusion, we found neither a preference nor avoidance in these butterflies. And notice how this is the way we typically write conclusions like this. I had the probability in here, 0.393, and the number of trials n. Okay, so we'll look at one other example here, if hopefully the thing hasn't stopped. Okay, let's look at the fritillaries, just to see what's going on with them. This is just another example very similar to the one I just did. So fritillaries, they're a lot more common than the monarchs. There's like 40% of these things. But watching the roses, we only count 22 of them, which is kind of low, because the mean here of this would be a little different, right? It would be 0.4 times 80, which is 32. So this is like 10, a count of 10 lower, all right? So how would we do that? All right, well, let's model that one, okay? So this time we're going to have a higher probability, 0.4, all right? Okay, now here in the middle, 32, that's the mean again. This time we only counted 22. So again, if we wanted the probability of getting exactly 22, what is that? Recalculate. Wait a minute, something is fishy here. Oh, I hit the wrong button, that's why. Okay, notice that's really low. But again, remember, that's pretty meaningless because, what we're interested in is if they're avoiding or preferring the butterfly, the flowers. So what we're going to need is we're going to need below 23, right, because we want 22 in there. And then at the other end, so you take 32, add the 10 to it, and you get 42 at the other end. We're going to need, so wait a minute, we need below 23 and we need above 41. Okay, so there's that end of the distribution. Notice it's pretty small. And then click up here, you have the other end of the distribution. So what we need to do to get the total of those things is you add them, of course, here. All right, that's what I did over here to get that probability. So that's still pretty low. What that means is, to get a really extreme value like 22, or at the other end, 42, to get extreme values like that, if these butterflies are going at random, it's unlikely. It's unlikely to get extreme values like that. So the butterflies seem to be doing something. You know, they're not going to the flowers at random because the probability is really, really low that they're doing that at random. So we need to figure out, well, what are they doing? Do they prefer them, in which case we'd expect it at this end, or are they avoiding the roses, in which case it'd be at this end? Looks like it's at that end, right? That's where we found it. It was over there. So it looks like they're avoiding them. So this is how you would write that. All right. Conclusion, fritillaries seem to avoid roses. And here's the probability that we found by adding the two ends. And that's in 80 trials. Okay, so we'll conclude this video here.